Right, in number 7, we are asked to write a base 9 number in expanded notation and then convert it to what we would consider to be base 10. Okay, so first I want to count how many positions there are. 1, 2, 3, 4, which tells me I'm going to start with 9 to the 0th power, 9 to the 1st, 9 squared. Sorry, there's a plus after that, and 9 cubed. Okay, so each of those numbers represent one of those positions. So 6, 5, 2, and 3. Okay, so then I want to go to my calculator and just type that in. This is what, by the way, we would consider to be expanded notation. So then 6 times 9 cubed plus 5 times 9 squared plus 2 times 9 plus 3 times 9 to the 0th. And we should get, I'm getting 4,800. Okay. All right, moving on. Number 8, find the numeral preceding and succeeding the following. So in other words, we're going to count, and we're going to count what number came before this one, what number came after this one. So we're in base 7, and one suggestion that I gave in class is just count out the numbers. So 0, 1, 2, 3, 4, 5, 6. Now I want to write 7, but because we're in base 7, that actually just gives us another placeholder, just gives us another digit in the pattern. So I start off at 1, 0, 1, 1, 1, 2, 1, 3, 4, 1, 5, 1, 6. And I want to write 7, but I'm not. I'm going to count another place value. So 2, 0, 2, 1, 2, 2, 2. Okay. At that point, I'm going to stop because I hopefully think we get the point. And I'm going to look at the 0 position. So notice, after all of the zeros, if I look at the number after it, they all had a 1 in it. So that meant the number after 460 is 461. And then similarly, I'm going to look at the number before it, and notice they all have 6's in them. I guess what we consider to be the tens position went down 1. So it would be 4, 5, 6, base 7. And so that was the number before and the number after. All right, at number 9, we're asked to find the GCD and LCM of two numbers using a very specific method called intersection of sets. So first thing I need to do is I need to write out the prime factorizations of these numbers. So 20 is 2 times 10, and 10 is 2 times 5. So 2 times 2 times 5 happens to give me 20. And then I'm going to do the same thing with 50. So 50 would be 2 times 25, which is 5 times 5. Okay. So in the intersection of sets method, I'm going to break up my numbers as such. So the first rectangle, which I'm going to do in red, are things that multiply to give me 20. And the other rectangle, which I will do in blue, are things to multiply to give me 50. So I'm going to start with the overlap. I notice they both have 2's in them, and they both have a 5 in them. And so I'm going to write whatever's left in the other side. And so what that says is that 2 times 2 times 5 happens to give me 20. And then the 50 is missing a 5. Okay, now this middle piece, I'm going to switch colors here. That is what we call the GCD. So the GCD would be 2 times 5, or 10. If I look at everything, so if I look at all of the numbers, so 2 times 2 times 5 times 5, that's what we call the least common multiple. So that would be the LCM is, I believe, 100. So there you go. GCD is 10, LCM is 100. All right, right below it, we're going to talk about properties. And I'm just going to caution you, this is an area that I see students lose points on that Just make sure you know the names and know how to describe them. I'm actually not taking off for spelling, but you got to get close. You got to be kind of close to what the property is. Okay, so in this first one in A, what's changing? So I start off with 1 times 5 times 3, and the 1 disappeared. Okay, so what I want to think is what property involves multiplying by 1, and that's what's called the multiplicative identity. So I'm okay if you abbreviate it as multiply identity instead of spell out the word multiplicative, but that's the general idea. Second one is I have 5 plus 4 times 9 plus 2, and I somehow managed to split up the 9 and the 2 and change it into a sum. So I'm multiplying the 9 with each of the 5 and the 4s, and the 2 with the 5 and the 4, but somehow my product became a sum. That's actually a distributive property. It's a very clever distributive one, but it's it's not what we normally would associate with that, but that's an illustration of that particular property. C, A plus 0 is A. So what happened? I'm adding 0, and so that's what's called the additive identity. Sorry, an identity. And then the last one, A plus B equals B plus A. So I'm adding two things and I'm switching places. That's the commutative property of addition. Okay. So again, I'm not necessarily taking off for spelling, but you do kind of get kind of close to the title in order for that to make any sort of sense. So, but I would strongly recommend that you go look up properties and make sure you can recognize the different forms of them. In number 11, I'm asking you to demonstrate evidence of the divisibility rules. So I don't want you to type it in a calculator and simply say, yes, 2 goes into it or 3 goes into it. I want you to show me where do I look in the number without a calculator to make that decision. Okay. So in other words, let's start with 2, for example. I don't need to look at all of the digits to decide if 2 works. I can just look at the very last digit. And since 2 does not go into 1, it's that last digit there, then I know 2 does not go in the whole number. And so that's sufficient for me. That's all I need to know is the number I'm testing, whether it goes in or not go into, whatever the rule is, and then just tell me what the conclusion is. Okay, so give me all that. That's enough evidence that you've mastered this. Let's go to 3. So in 3, I want to add up all of the numbers. So 3 plus 6 plus 9 plus 7 plus 4 plus 1, and that's going to give me another number, and chances are I'm going to have to add up each of those again. Let me kind of think this out loud here. So 3 plus 6 plus 9, that's 18, plus another 7 puts me at 25, plus another 5 puts me at 30. Okay, so I have 30 there. Now I could stop here and I could test 30, but I can also keep going to do 3 plus 0 gives me 3. Now, does 3 work? Yep, 3 goes into that, so that's a yes. 3 goes into it. I'm just going to keep going in order here. And on the number 4, I want to look at the last two digits, I'm sorry, which are 4 and 1, so 41. And so I know 4 is not going to work in that because 4 goes into 40 but not 41. So 4 is not divisible into the number. 5, I'm going to look at the last digit again, and it's either got to be a 0 or 5, and so it's a 1, so that's a big no for that. 6, okay, so since 2 was a no and 3 was a yes, 6 is going to be a no. In order for 6 to go in, 2 and 3 both have to go in. 8. Okay, 8. We're looking at the last 3 digits. Okay, so you might have to kind of actually test that. Let's see, so 8 goes into 74 9 times. I knew that. 72. So 4 minus 2 is 221. That's not going to work, because it doesn't go in there evenly. Because I can get it a 2, but it doesn't matter, because I'm going to get a remainder of something. So I know 8 doesn't go into 741. So 8 doesn't go into the number also. So there's a no for that one. All right, 9. Well, the rule for 9 is to add up the digits again. I already added them up and I got 30. And I know 9 does not go into 30, so 9 does not go into that. 10 is look at the last digit. And since 10 does not go into 1, then I know it doesn't work. And then our 11 rule. Okay, 11 rule is we got to look at every other one and add those up. So 1, 7, see if I get that right, 1, 7, and 6. So 1 plus 7 plus 6 is going to give me a number. And go the other route, so 4, 9, and 3. So 4 plus 9 plus 3. Okay, so let's see what we get when we add those up. I get 14 for one of them, and I get 16 for the other. Okay, so then I want to subtract, and that's what I'm going to base my decision off of, is the difference from the biggest from the smallest. Now, I know 11 is not going to go into 2, so I know 11 doesn't work in that. If I get a 0 is an indication that 11 does work. But anyways, so that's what I'm testing you on this question, is tell me just minimum standard-wise, where do I look to decide if it goes in, and then what's the end result? Was it a yes or no on each digit? All right, number 12, apparently I liked number 12 so much I wrote it twice. Sorry about that. So in number 12, we're looking at an illustration of the Euclidean algorithm. This is where I divide two numbers and I focus on the remainder and just keep looking for how many times it divides in there evenly. So I'm going to start with 365 412 over 1255. And again, I want to focus in on the remainder. So let me divide that out. All right, so I got 291 with a remainder of, and just multiply that real quick, remainder of 207. Okay, so that's what I want next. I want the 1255 divided by 207. So 1255. Okay, so I get 6 with a remainder of 13. Okay, let's keep repeating. I get 207 divided by 13. Goes in there 15 times with the remainder of, which I will tell you in a second. A remainder of 12. Okay. So then I want 13 divided by 12, goes in there once with a remainder of 1. And I want 12 divided by 1, which goes in there 12 times with a remainder of 0. Okay, so in this case, because I got a remainder of 0, I want to look back at the last remainder that I used. And so that would be my GCD. So in this case, we would say that these two numbers are relatively prime, meaning they don't have any common divisors that work into either one of them. But anyways, GCD 1 in this particular case. All right, number 13, just testing a series of algebra properties and make sure we understand them both in a numerical sense and algebraic sense. So these are typical questions that would show up in an algebra type course. Oddly enough, I put this first one on there so that when students miss it, I know that there's a bigger problem. So 5 subtract a negative 3, as you got two negatives, make a positive, so it's really 5 plus 3, which is 8 in that case. B, okay. This one you got to be very careful on as far as how you break that down. So for example, I know that 2 goes into 32 16 times. And I know that 72, I break that into 36, 2 times 36. A cubed, okay. Now, if you're one that gets this stuff right, then you don't necessarily have to write it out, but if you need to see it, then this is why it works the way it works. A cubed is really A times A times A, and AB to the fourth is B, 4 B's in a row. Okay. All right, and then I'm going to look for things that I can divide out. I think I can still keep going with those 16 and 36. Let's see. I can take out another 2. Let's do that. If I divide by 2, I get 8 over 18. I'll take out another 2, which is 4 over 9. Okay, so that's pretty much done at that point. A cubed B. So one of my A's divides out, one of my B's divides out. Okay, so I'm left with 4 over 9 with the numbers. I have an A squared in the numerator and a B cubed in the denominator. So you should have a very simplified reduced form on that. Okay, question C, A squared plus B squared over A plus B. Okay, I'm just going to say this is wrong. Don't do this. But I saw a lot of students do this where they factored it, A plus B, A minus B, and they crossed it off and they wrote A minus B, and they were so proud of themselves, and it's 100% wrong. Please do not do that. Okay, this actually is not factorable. We cannot reduce this any further than it is. That is the simplest form that it can get in. In question D, we are simplifying this expression by using common denominator. So our common denominator, kind of looking here at the bottom, I'm going to rewrite this sort of a different way that might help us see. I've got A times A and B times B for the first fraction. So that means my common denominator's got to have at least an A squared in it, and it's got to have a B squared in it. Okay, so then I'm going to look up in the numerator and multiply by what was missing. So in the 3, for the 3's case, there's nothing. So I'm just going to bring that over. And in the 5's case, it was missing an A. So I'm going to bring that over. And then that's it. There's nothing we can divide out. There's nothing to simplify. So that is the most correct form the simplest form that we can get this thing into. Okay, number 14, true false. This particular idea is brutal. I still have students that like to show me true statements and then give that evidence of why it's true. That's not the intention of these type of question. The intention is to find a counterexample if possible, and then state that it's false. So if it's not a defined rule, then we need to have a counterexample. Okay, so number 14, the absolute value of x cubed equals x cubed. Okay, so what I'm going to do is I need to test things that absolute value would have issues with. For example, negatives. So let me just pick a value for x. Let me say that x is equal to -1. And let's just test and see if I take -1 cubed, the absolute value, does it in fact equal -1 cubed? Okay. Now notice I'm testing -1, so I put parentheses around my entire -1, including the negative. Now, absolute value of -1, so -1 cubed is -1. Again, question marks because I don't know if it's true or not. That actually gives me -1, but what does absolute value do? It makes everything positive. Okay, so right there, there's evidence that it's not true for the number -1. It might be true for other things, but I found a counterexample. So this is false, and there's my justification. There's my rationale on that. So in order to get full credit, you need to first identify whether it is true or false, and then you need to have a good rationale, some sort of true statement or false statement that justifies that. All right, B, for all x and y, the absolute value of x plus y is equal to the absolute value of x plus the absolute value of y. Again, let's test this with some negative numbers. Let's go x is -1 and y is -3. Let's test that and see what happens. So the absolute value of -1 plus -3 is the absolute value of -4, and that gives me 4. Okay, on the other side, absolute value of -1 plus the absolute value of -3. It's going to give me 1 plus 3, so I get 4 again. Okay, well, I tried something. It didn't work out for me. Let me modify my number. Let me switch one of these to be a +1, and let's see what impact that has on the overall math here. All right, +1. Here we got +1. All right, so inside the absolute value, I have a -2 this time. So that actually works out to be +2. And here, this works out to be 1 plus 3, which is 4. Those are not equivalent. Okay, so that is false. And there's my specific example illustrating this. Okay, C. All right, this was a huge concern. I had a lot of people that I think might have understood it correctly, but because of their justification, I couldn't tell if they were justifying their conclusion correctly. So I have to start with the idea that A is less than -B. So in other words, if I'm going to find a counterexample, then I need to pick A's and B's where that statement is in fact true. So let's talk about -B for a second. If I make B a negative number, and let's just go with 0. Why not? All right, so did I find something that fits this statement if A is less than -B? So if 0 is less than -3. Okay, again, notice I'm saying B is -3. So when I evaluate this, a -3 puts it at a +3. So is that in fact true? Well, yeah, that is. So, okay, I've got two numbers that fit this pattern. Now, consequently, is A less than 0? So is 0 less than 0? That's actually false. And so the two sets of numbers that I did are good counterexamples to why it's false. That is not to say that everything is going to be false, so please watch out for something like that. Here in D, that's actually a rule for subtracting fractions with a common denominator. So that's a true statement. On E, okay, E, I actually want to find a common denominator and actually work the math out here. So the common denominator would be 5 times 6. So that would be 1 times the piece that's missing, which is 5, plus the other one, which is 6 over 5 times 6, which 6 is divided out, and I'm left with 1/5. That's actually true. But you got to have a good understanding of fraction rules, especially common denominators, to demonstrate why it is true. And then lastly, for this, at least for this one, is the parentheses -x to the -2 power is equivalent to -x to the -2 power. So in other words, do the parentheses make a difference? And again, what's going to help us see this is if we pick a negative number. So let's take something like -3. Okay, so on the left side, I have a -3 raised to the -2. And I'm going to simplify that down, and then we'll come and look at the right side. Well, a negative, make that a positive, so 3 to the -2. And what does a negative exponent mean? That means we are dealing with a fraction. So 3 squared is 1/9. Okay, so that's the left side. The right side, okay, this time We have a negative on the outside, and the -3 part is going to go in the parentheses. It's going to go inside the term x. So in other words, the negative's on, so the negative is the last thing that we're going to deal with and see if that makes a difference. Well, what do we do with the -2 part of the exponent? We're going to put that in a denominator. And -3 squared is actually 9, and then we put the negative out front. Well, notice those are not the same. So this, in fact, is false. Okay, but you got to be very careful with this and make sure that you don't make any unnecessary assumptions to show if something's true or false.